Okay, this is Applied Calc 2, Checkpoint Quiz 6. Part 1, we're asked to find the area of the region bounded by these two curves. So, first thing we have to do is try to get a sketch of the situation. Y equals x is something we're very familiar with. Y equals x cubed is something you might not be so familiar with. In college algebra, you talk about odd degree polynomials. So it has an S shape to it since it's an odd degree, but you might not be sure exactly how that looks in there. And really, that's the important thing. Because when we find the area between curves, we need to always integrate the top curve minus the bottom curve. And it's tough to tell from this rough sketch who's on top, who's on bottom. So what do we do for that? We find where they intersect, and then we plot points. So we're trying to find the places where the curve y equals x cubed intersects the curve of y equals x. So we'll set x cubed equal to x. It's tempting at this point to divide both sides by 0, but you'll see why we don't want to do that. Let's bring everything over to one side and factor. There's an x in common I can pull out. I'm left with an x squared minus 1, and that factors as the difference of squares. So x minus 1, x plus 1. And so we get three answers. Either x itself is 0, x is 1, or x is negative 1. Now to figure out which y value goes with these x values, we can go back to either of these two equations. These are the x values where they cross. So if I plug 0 in, I should get the same answer out from this equation as I do this equation. So no matter how you do it, when x is 0, you get y is 0. When x is 1, you get y is 1. When x is negative 1, you would get y is negative 1. And so these are the intersection points. So to get a better graph of what's going on, we can go over here to our x and y, and we can plot these points. Here's 0, 0, negative 1, negative 1, 1, comma 1. Now we know the line y equals x goes through those points in that fashion. To figure out what the y equals x cubed is doing, we can plot points around here. If I plug in negative 2, for example, I'm all the way down at negative 8. If I plug in something between negative 1 and 0, for example, negative 1/2, negative 1/2 cubed is negative 1/8. If I plug in negative 1/2 to y equals x, I get negative 1/2. So this is closer to the x-axis than the line. I can plug in y equals positive 1/2. If I plug it into the y equals x cubed, I get positive 1/8, which is going to be smaller than 1/2, which is what I would get on that line. And then if I plug in 2, I'm up at positive 8. And so we can connect the dots then. And so that's the familiar S shape of that y equals x cubed. So when they're asking for the region bounded by the curves, they're talking about this part here and this part there. So remember, area between curves, you integrate a to b, top minus bottom. In our first part, the x cubed is on top and the x is on the bottom. So that's the integral from negative 1 to 0, top minus bottom, x cubed minus x dx, plus between 0 and 1, x is on top. So it's x minus x cubed dx. Now, this integral, or these areas, happen to be symmetric. In other words, they're congruent areas. So if you find the integral area of one of these and double it, you should get the area of the whole thing. And you can actually see that happen if you take the time. In both of these, the antiderivative, I get x to the 4th over 4 minus x squared over 2, evaluated from negative 1 to 0. Here I would get x squared over 2 minus x to the 4th over 4, evaluated from 0 to 1. Plug in and do the machinations here. You're going to get 0 when you plug the zeros in. When you plug in the negative 1, you'll get 1/4 minus 1/2, which is negative 1/4, but it's being subtracted. Here, when you plug in the 1, you're going to get 1/2 minus 1/4. So when the dust settles, you're going to get a grand total of 1/2. So 1/2 is the area bounded by these two curves. And that'll do it for number 1.